Welcome to AI Paper Podcast, where we distill the cutting edge of AI research into clear, actionable insights for you. Today, we're plunging into a truly significant paper from ByteDance Seed, UI-TARS-2, Advancing GUI Agent with Multi-Turn Reinforcement Learning. And trust me, this one is quite the game changer for anyone working with intelligent agents. So in a nutshell, UI-TARS-2 is this groundbreaking GUI agent. It can natively interact with pretty much any digital interface. We're talking desktop, mobile apps, web browsers.
And even games, complex ones too.
Right. And it's getting surprisingly close to human-level performance on some tasks. The secret sauce, it seems, lies in its very systematic training approach.
Exactly. Its success really stands on four core pillars, these innovations. First, there's this self-improving data flywheel. It basically generates high-quality training data continuously. Second, they developed a highly stable multi-turn reinforcement learning framework, which is crucial for those really tricky, long-horizon tasks. Third, a truly hybrid GUI environment. It's not just clicking buttons, it integrates real-world tools like file systems and terminals.
Oh.
And finally, a unified, scalable sandbox platform. This is key for doing massive, robust training runs.
And the results are pretty remarkable, right? This isn't just some small incremental improvement. It's significantly outperforming established baselines. Think Claude, OpenAI agents across a whole range of benchmarks, complex information seeking, even practical software engineering tasks. It feels like a real leap forward for generalist agents.
Okay, so let's really dive into what makes UI-TARS-2 tick, what makes it so powerful. For a long time, this dream of a truly autonomous agent, one that could just seamlessly navigate our digital world like we do, well, it's felt a bit like science fiction. Building agents for graphical user interfaces, GUIs, it's been this incredibly exciting frontier in AI, but also really challenging.
Oh, definitely.
I mean, it's one thing to process text, right? But it's totally different to interact with this dynamic visual world of buttons, menus, subtle feedback. And the paper really lays out those challenges quite clearly. Think about it. Data scarcity, that's a huge one. Unlike text, where we have enormous data sets, getting detailed, high-quality interaction trajectories, showing the agent's reasoning, its actions, the environment state, the feedback, it's incredibly expensive and just time-consuming to collect. Then you've got the complexity of scalable multi-turn reinforcement learning. When tasks take many, many steps, the rewards are often sparse or delayed.
Right, the credit assignment problem.
Exactly. Makes it super hard for the agent to figure out, okay, what did I do right like 10 steps ago? Optimization gets unstable. Assigning credit over these long sequences is, well, it's a nightmare. Plus, most real-world tasks aren't just about clicking things on a screen.
Yeah, that's true.
You might need to pop open a terminal or look inside a file, maybe even call an API. Pure GUI operation is just too limited for a lot of practical stuff. An agent needs more tools.
A bigger toolkit.
Precisely. And then there's the sheer engineering lift. Deploying robust, reproducible, fault-tolerant RL environments at massive scale for training. That's a huge operational headache for any research team.
Wow. Yeah. It sounds like a perfect storm of difficulties, really. But I guess this is exactly where UI-TARS-2 comes in. ByteDance Seed seems to have tackled these specific challenges head-on, offering a pretty comprehensive solution that moves us quite a bit closer to that truly generalist GUI agent. So one of the most elegant solutions they talk about is this data flywheel. Sounds intriguing. It's not just data collection, is it?
Not at all. It's much more clever than that. It's this self-reinforcing cycle where the model and the data actually co-evolve. They improve each other continuously. It's their answer to that fundamental data scarcity problem we just talked about.
Okay, so how does this flywheel actually work?
Right. Think of it like a learning engine that fuels itself. It operates in three interconnected stages. First stage, continual pre-training, CT. Here, the model just soaks up broad knowledge from massive, diverse data sources, online tutorials, videos, their own in-house data. This gives it a solid foundation.
Okay, like a general education.
Exactly. Then, stage 2, supervised fine-tuning, SFT. This is where it learns high-quality, task-specific instructions. Think expert demonstrations, carefully curated examples.
Anything more specific.
Right. And finally, stage 3, reinforcement learning, RL. This is where the end-to-end optimization happens. The agent learns directly by interacting with verifiable tasks in the environment and getting feedback.
Okay, CT, SFT, RL. But where's the flywheel part? How does it loop back?
This is the really clever bit. The latest, most capable RL model isn't just used for evaluation. It's put to work generating new interaction trajectories.
Oh, I see.
The really good trajectories, the high-quality ones it generates. They get promoted back into the supervised fine-tuning stage. So it's refining its own gold standard data.
And the less successful ones.
Instead of just throwing them away, the lower quality outputs get recycled back to enrich the continual pre-training data set. So this iterative loop means the model literally gets better at generating its own high-quality training data over time. It creates this continuous upward spiral of improvement for both the model and the data.
That is clever. It's like it's teaching itself to be a better student.
You could put it that way, yeah. And the way they prepare this data is also quite advanced. For that initial continual pre-training, they use something called in situ annotation. They have human annotators perform real tasks on their own computers using a think aloud protocol. So they're verbalizing their thought process every step.
While they're doing the task.
Exactly. And these verbalizations are transcribed and then automatically aligned with their UI actions, clicks, typing, etc. They even use two groups: experts doing complex, specific tasks, and novices whose data captures more exploration, maybe some fumbling around, problem-solving behaviors, gives them a really rich, diverse data set.
Okay, that makes sense for the broad pre-training. What about the fine-tuning, the SFT stage?
For SFT, they came up with an interactive annotation framework. This is really neat. It's a human-in-the-loop system. Annotators provide online supervision inside a controlled VM or browser. As the model suggests an action, the human annotator can either say, yep, good move, accept it, or they can override it in real time saying, no, do this instead.
Okay, so the human corrects it on the fly.
Precisely. And this is critical because it ensures the data generated is on policy. The model learns from the kinds of situations and mistakes it actually makes, which drastically helps it generalize better later on. It avoids that classic problem of traditional offline SFT, where the model only sees perfect examples and struggles when it goes slightly off-piste.
That seems like a huge step towards making these agents genuinely adaptable, learning from dynamic, real-world-like interactions. But adaptability isn't just about the data, right? It's also about the range of environments the agent can handle. And UI-TARS-2 addresses this with what they call the all-in-one GUI Sandbox. Sounds like it gives the agent a much bigger playground.
Absolutely. They've essentially built a whole digital ecosystem for UI-TARS-2. There are two main environment types within this sandbox. First, the main GUI environment. This uses cloud virtual machines running standard OSs like Windows, Ubuntu, even Android mobile OS.
Wow, okay.
And it integrates tools like PyDo-GUI for desktop control and ADB for Android interaction, allowing for seamless cross-device operations within the same session. The scale here is pretty impressive too.
Awesome.
We're talking a VM cluster with thousands of instances, capable of handling thousands of queries per second. This allows for truly massive scale training and ensures reproducibility. Crucially, this setup means the agent can do complex, real-world workflows, like download a file using a web browser, then switch over and process that file using shell commands in a terminal, all within the same container instance because they share a file system.
That's powerful, bridging the gap between apps and system tools.
Exactly. And then for games, they built a specialized hardware-accelerated browser sandbox. This is tailored for web-based mini-games, HTML5, WebGL stuff. It enables high concurrency by running multiple browser instances per container. It's got built-in crash recovery, page management, checkpointing for reproducibility, and to speed things up. They use GPU hardware acceleration to reduce the overhead of taking screenshots constantly. And they even have a fake clock that can manipulate time within the game environment, speed things up for training efficiency without actually breaking the game's logic. It's a highly optimized RL playground specifically for the web stack.
Okay, so you've got these incredibly rich dynamic environments, you've got this self-improving data flow, but how does UI-TARS-2 actually learn those super complex multi-step reasoning skills? What's the secret sauce for mastering these long horizon tasks?
Right, that's where their sophisticated multi-turn reinforcement learning framework comes into play. It's built on something they call RLVR reinforcement learning with verifiable rewards. This is really the core intelligence. They put a massive amount of effort into task design. For GUI browsing tasks, for instance, they have an automated pipeline that generates incredibly complex information-seeking challenges.
How complex are we talking?
Well, they use techniques like multi-condition obfuscation, where key information is hidden, forcing the agent to be indirect, and multi-hop chain-like conditions, where it has to follow links, gather info from multiple pages sequentially. For more general web tasks, they synthesize scenarios across nearly 700 diverse websites. And for gameplay, it's a mix of public HTML5 WebGL games plus LLM-synthesized games, all instrumented with JavaScript verification scripts to precisely track scores and game states.
Okay, smart task design. What about the rewards? How does it know if it's doing well, especially on those tricky multi-step tasks?
Yeah, the reward design is crucial. For tasks where the outcome is clear-cut, like winning a game, or finding a specific piece of information that can be checked, they use simple binary correctness. Did it succeed or not? Or sometimes an LLM as judge approach to evaluate the result.
Makes sense.
But for the more open-ended, non-verifiable tasks, like just generally navigating a website to achieve a fuzzier goal, that's where UI-TARS-2 gets clever again. It actually uses itself as a generative outcome reward model, ORM.
It rewards itself.
Sort of. A component of UI-TARS-2, the ORM, is trained specifically to predict a scalar reward based on the agent's actions, the text history, and the screenshots it sees. It learns to judge the quality of interaction sequences, even when there's no external ground truth.
Okay, that's interesting. And how do they manage the sheer scale of this RL training efficiently?
They use an asynchronous agent rollout via stateful environment. It's a smart architecture. It basically decouples the agent's thinking, the inference part, from the actual execution in the environment.
Right, so they don't block each other.
Exactly. This allows for real-time online server mode processing, which is more usable. They also use streaming training with partially filled rollout pools. This means training can start as soon as enough complete interaction traces are ready, rather than waiting for the absolute longest ones to finish, which avoids bottlenecks. And, critically, the stateful environment integration means the agent keeps its context, its memory, across multiple tool uses and steps within a complex task.
Okay, so the base algorithm is PPO, Proximal Policy Optimization, which is pretty standard for RL. But I imagine just vanilla PPO would struggle with these incredibly long, complex GUI interactions. Do they have to add some special sauce on top?
Oh, absolutely. You hit it exactly. Standard PPO would likely buckle under this kind of sequence length and complexity. UI-TARS-2 basically supercharges PPO for these long horizon tasks. For one, they use reward shaping. The agent doesn't just get a reward at the very end if it succeeds. It gets smaller, intermediate rewards for making good progress, for efficiency, for correct formatting. Think of it like guidance along the way.
Okay, nudging it in the right direction.
Precisely. They also use more advanced techniques to handle value estimation over long sequences, like decoupled GAE and length adaptive GAE. These are sophisticated ways to ensure the agent properly assigns credit to actions taken way back at the start of a long task, preventing the value signal from decaying too much.
Right, maintaining that long-term perspective.
Exactly, and to make training more stable right from the get-go, they pre-train the value model offline. This gives the agent a much better initial estimate of how good different states are, avoiding some common RL instability issues. They even use a modified clipping mechanism in PPO called clip higher to encourage a bit more exploration.
So these aren't just tweaks, they sound like pretty significant enhancements to make PPO work in this domain.
They really are. Critical engineering to make it practical for these frontier agent tasks.
Okay, that makes sense. Now, another big challenge, I think, for generalist agents is combining skills. How do you get an agent that's good at web browsing and desktop apps and maybe games without having to do this massive, potentially unstable retraining on everything at once? UI-TARS-2 uses something called parameter interpolation. How's that work?
Yeah, it's a really elegant approach, actually. The core idea comes from the observation that models fine-tuned from the same starting checkpoint often end up in parameter spaces that are linearly mode connected. Meaning you can basically average their weights. So you train specialized expert agents independently, one for GI browsing, one for games, maybe one for using system tools via an SDK, train them really well in their domain. And then to create the generalist agent, you simply merge their learned parameters using a weighted sum. You literally average the weights of the expert models.
So you don't need that massive joint training phase.
Exactly. You get strong cross-domain generalization, the ability to handle tasks from different areas without the huge computational cost and potential headaches of trying to train one giant model on wildly diverse data distributions simultaneously. It's a very efficient way to scale capabilities.
That is neat. A practical shortcut to generalization. All right, let's get to the payoff. The proof in the pudding, as they say, the experimental results and the practical insights. The numbers for UI-TARS-2 look really strong.
They really are, across the board. On standard GUI benchmarks, you see scores like 88.2% on Online Mind 2 Web, 47.5% on Osworld, 50.6% on Windows Agent Arena, 73.3% on Android World. These are significant jumps over strong baselines like Claude and OpenAI's agents.
And that SDK integration you mentioned, did it make a big difference?
Huge difference. Integrating system-level tools like the terminal allowed it to score 45.3% on Terminal Bench, 68.7% on SWE Bench, which involves software engineering tasks, on a benchmark called Browse Compen, just giving it SDK access boosted performance from around 7% to nearly 30%. It shows that for complex, multi-tool tasks, just clicking isn't enough.
Right, you need the full toolkit.
Exactly. And what's also really interesting is the out-of-distribution generalization.
Meaning how well it handles things it wasn't explicitly trained on.
Precisely. Even though a lot of the RL training was focused on browser tasks, the resulting agent showed significant performance gains when tested on OS World, the desktop environment about 10.5% better, and on Android World about 8.7% better.
Wow.
This strongly suggests the interaction skills it learned are genuinely transferable, not just specific to the web tasks it trained heavily on.
And the games.
Yeah, on the game benchmarks, it achieved a mean normalized score of almost 60% of human-level performance across 15 different games. That significantly beats OpenAI's CUA and Claude computer use by like 2.4x and 2.8x.
Right.
It's genuinely competitive with other frontier proprietary models on benchmarks like LM Game Bench.
Okay, so the headline results are impressive. But beyond the scores, the paper dives into some really unique practical insights from the training process itself, right? What were some of the key takeaways there?
Yeah, this is where it gets really interesting for researchers, I think. One of the most counterintuitive findings was about training rewards and entropy.
Okay.
Normally in RL, you expect the agent's entropy, basically its randomness or exploration level, to decrease as it gets better and converges on optimal strategies.
Right, it becomes less random, more focused.
But with UI-TARS-2, particularly in the GI and game tasks, they observed rising entropy during training, even as rewards were going up.
That is weird, so it got better and more exploratory.
It suggests that for these complex, visually rich environments, the agent actually benefits from maintaining or even expanding its exploration space. It's constantly finding new ways to interact, new patterns. Like a human learning a complex piece of software, you don't just find one way and stick to it rigidly. You poke around, discover shortcuts, new features.
Huh. So maybe for these kinds of agents, constant exploration isn't a bug, it's a feature for adaptability.
That seems to be the implication. It challenges the traditional RL view of just exploiting the known best path. Maybe we need to design training curricula that embrace this ongoing exploration.
Fascinating. What else did they uncover about the agent's learning process?
Another really interesting point was the viability of VLM as verifier. Remember that outcome reward model, ORM, it uses for tasks without clear ground truth?
Yeah, the one it uses to reward itself.
Well, they found that even though their ORM wasn't perfect, it had about an 84% F1 score, meaning it made some mistakes, some false positives. It was still highly effective for driving the RL training.
So an imperfect judge was good enough?
Apparently so. The hypothesis is that even if the ORM gets the final outcome wrong sometimes, the agent still gets appropriate rewards for all the correct intermediate steps it took along the way. And these positive signals largely outweigh the occasional noisy or incorrect final reward. This is super important practically because getting a perfect reward signal for complex real-world tasks is often impossible.
That's a really pragmatic finding. What about efficiency? Did the agent get faster or smarter over time?
Yes, they tracked the average think length. In the GUI tasks, the amount of thinking time per step actually declined as training progressed. So it got more efficient, needing less deliberation to achieve the same results.
Okay, learning shortcuts.
Kind of. In games, though, the pattern was periodic. Think length would increase when the agent hit a new, harder level, then decrease again as it learned to master that level. It shows this nice interplay between task difficulty and the agent's cognitive effort. It adapts its thinking budget to the challenge.
Makes sense. And any insights for actually deploying these models? Latency is always a concern.
Definitely. They looked at quantization for latency reduction. They applied W4AA quantization, which basically compresses the model to make it run faster.
And did it work?
Yeah, it significantly boosted the token generation rate, almost doubled it, and cut the latency per interaction round nearly in half, from 4 seconds down to 2.5 seconds.
But what about performance? Usually quantization hurts accuracy?
There was a drop, but it was pretty modest. On OS World, accuracy went from 47.5% down to 44.4%. So a small hit for a big speed up. This makes UI-TARS-2 much more practical for real-time, latency-sensitive applications, moving from the lab to the real world.
That's a crucial step. Okay, what a fascinating deep dive into UI-TARS-2. So just to recap, this paper from ByteDance Seed really presents a robust GUI-centered agent. It can navigate this wide range of real-world interactive scenarios, desktop, web, games, and crucially, it shows strong generalization. That's key for any agent we'd actually want to use.
Absolutely. And beyond just the impressive scores, it's the systematic methodology that's so valuable. That data flywheel concept, the stable multi-turn RL framework, the hybrid environments, the unified platform, combined with the deep insights they got from analyzing the training dynamics, it really provides crucial principles for anyone building generalist agents going forward. This work genuinely charts a practical path.
So wrapping up, what does this all mean for you, our listeners, the researchers, the engineers building the next generation of AI? UI-TARS-2 really shows us a clear path toward that vision of a truly unified digital agent, one that isn't just stuck inside a single app or platform.
Yeah, think about this. As these GUI agents get more capable, as they integrate more seamlessly across operating systems, across different applications, maybe even jumping into game environments, what new kinds of human-computer interaction does that unlock? Can we really see a future where an AI assistant genuinely understands your context and anticipates your needs across all the digital things you do, learning your workflows, adapting to new software, things we've only really dreamed about?
It opens up huge possibilities.
For productivity, for accessibility, even for entertainment. But it also raises big questions, right? What are the challenges, the opportunities, when our digital tools, our digital companions, can navigate our complex interfaces almost as well as we can, maybe even better in some ways?
It's definitely a future that feels much closer now, and UI-TARS-2 is clearly a major milestone on that journey. Thank you so much for joining us on this deep dive into UI-TARS-2. We definitely encourage you to check out the paper itself and really think about its implications for your own work in AI. Until next time on AI Paper Podcasts, keep building smarter.